So, okay, the recording has started. Good evening, everyone. Welcome to sixth week of analog electronic circuit. And this week we have learned about constant GM circuits. So we will try to build upon that and explore some further aspects of constant GM circuit in this tutorial. Before we begin the tute, is there any doubt in any of the material that has been covered so far?
Sir, screen is not visible, sir.
Yeah, I will share the screen now. But yeah,
Sir, I have one. Sir, I need a full-fledged question based on the full swing, sir.
uh, full swing. So you can take any circuit for that matter, and
Mm.
so you want to have questions on swing limits. You are saying, right?
Yes, sir. For example, if we take any circuit where we need to obtain a full swing and a maximum voltage, like that. Maximum voltage means we will consider both saturation condition and cutoff condition. So based on that peak voltage, we will calculate, no, sir, generally.
Correct. So yeah, that's what. So you want more questions on that, right?
Any one question if you solve means if I commit any mistake I will learn from that from you, sir, that's why.
Okay, so we can start with one of such questions. Let me think of something. So we can start with a basic structure of common drain amplifier. Okay.
Okay, sir.
Uh, what we can do is, so we have, let's say, an input source with Vi, which is connected through a capacitor to the gate of the circuit. The drain is fixed to VDS, VDD, and then we have this thing. Okay, and let us have it this way. So this is being biased, let's say using a 10 microamp circuit, 10 microamp current source with a current mirror. Okay. Let's say we have this circuit. Okay. We can so first of all, let me define some parameter. So let's say all the transistors have W by L equal to 1, W by L equal to 1, and W by L equal to 1, and mu n Cox equal to 100 microampere per volt square. Okay, so let's say these are the conditions given to you, or wait, this is let's say 100 microamp. Okay, and this is some uh, this is biased with some voltage. This is R and VDD by 2. VDD is, let's say, 6 volts. Okay, so this is the question. In this, you need to find out the gain from the gain of the circuit from input to output, and the swing limits over which this circuit will behave as all the transistors are in saturation, hence it will behave as the small signal analysis will hold true. So first of all, what is the gate voltage of which is the input transistor? Let's say
uh,
this is M1, this is M2, and this is M3.
M2, sir.
So M2 is the input transistor, correct?
Yes, sir.
And now, what is VG of M2?
VI, sir. Small VI.
No, no. In terms of in DC, what is VG of M2 in DC?
Okay. Six. Yeah, it would be three, sir.
3
3 volts.
volts, correct?
Hmm.
So Vg of M2, as 3 volts. Now, can you tell me, and let's say VTH of this is zero point 0.5 volts. Okay. So, can you tell me what will be the current flowing through the transistor M2, that is I of M2?
Yeah, it would be it would be same current, sir.
How much is it?
100 microamperes.
100 microamperes.
Hmm.
Okay. Now, you know that 100 microampere current flows through I of M2, and it's 100 microampere is equal to half.
Muon Cox, yeah, 100. 100 will get
Okay, let me do it for ease of calculation. Let it be 200 microampere per volt square. Okay, half into 200 microampere per volt square into W by L, that is 1 times VGS2 minus VTH, correct? Whole
Yes, sir.
square. Okay. So, from this, what is VGS2?
Yeah, 1 plus VTH, sir.
1 plus VTH, and VTH is zero point 0.5. Okay.
Mm, mm.
So VGS2 is 1.5 volts, correct?
Yes, sir.
Okay. VGS2 and what will be VGS3 and VGS1?
Uh,
Can you
yeah,
quickly tell me?
okay. Sir, VGS 1 and VGS 3 both are equal, sir.
And what is it equal to?
So based on the current, we can find no, sir. W L.
Yeah. So we just found it that if 100 microampere current flows through M2 and it is in
Mm,
saturation, your VGS is of 1.5 volts.
mm.
And same will be the case with VGS1 and VGS3 also, right? Because see, your yeah, correct. See, your all three transistors are identical. So say VGS for all of them will be equal. Is it clear?
Yes, sir. But my doubt is here we are cascading now. How it would be equal, sir?
Where we are cascading? We are cascading nowhere.
No, sir. M2 and M3 are cascaded, no, sir.
It's cascoded. Okay. But
Cascaded. Sorry, sorry. Yeah,
how will that create a difference? As long as there is no backgate effect, you understand backgate effect?
no, sir. I'm not able to explain.
As long as there is no difference in the as long as the threshold voltage mu and cox everything of the transistors M2 and M3 are same, you won't have any a difference in the current equation of transistor M2 and M3, right? Both are in saturation, both have same mu and cox W by L, both have same VTH, so their current their V, and both have same currents, so their VGS will be same, right?
Yes, sir. My question is here M2 and M3 are cascoded, no, sir. So,
Okay.
I mean, so the same source voltage, if M3 has some source, if it is not grounded, then it won't be equal, no, sir.
No, I'm not talking about only the gate voltage. I'm talking about the voltage difference. That is this voltage. This is
Mm,
VGS. This
mm.
is VGS.
Yes, sir.
These two will be same. The voltage difference between gate and source will be the same. That's what I'm saying.
Yes, sir. Yes, sir. Yeah, getting,
Okay.
sir.
Okay. So in DC, this is at 1.5 volt. And what is the voltage at this node?
Uh, yeah, it would be zero point 0.5, sir.
What was the voltage at this node?
Yeah, it is 3 volt, 3
3
volts.
volts. Correct.
Mm, mm.
What is the voltage, DC voltage at V naught node?
Yeah, 3 minus.
What was the
Yeah,
VGS of?
yeah, 1.5, sir.
Okay, so this is at 1.5. Okay,
Mm.
Now you tell me, while like assuming this capacitor, this coupling capacitor is large enough for the like frequency of interest, that so that in the frequency of interest this capacitor is shorted. So in that case, can you quickly tell me what is the gain from input to output?
Mm, okay, it should be minus GM into.
Will there be a minus in it?
Oh, no, no, sir. It is drain, right? No, no, it won't be. It should be one. Sir, we need gain. It should be unity only, common drain. But we need to write the equation. Then only it will be.
Yeah. So, what is the gain? Gain of a common drain amplifier. Let's say there was some 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 resistance at the source of the common drain for RS. So, what is the gain from input to output in common drain amp? It is like this, right?
Yes,
You
sir.
have input over here, you have some RS over here, and you take the output over here. What is V over VO by VI? And you have some GM.
It should be approximately VA, sir. But uh, there would be equation now.
You should remember this equation. It's GMRS upon 1 plus GMRS. This is something that if you remember, you can do calculations of gain of a large circuits quickly. Okay.
Yes, sir.
Now, in this case, since there is no channel length modulation, can you tell me what is RS?
Yeah. Sir, RS is nothing but um, M3, right? M3 resistance.
Yeah, there is no channel length modulation. So, what is the value of RS? Infinite, correct. So, if the value of RS is infinite, this VO by VI is equal to 1 if RS tends to infinity. So, now you know the gain from input to output. You know the DC voltages of all the nodes. Now, you need to find the swing limits. So, looking at the circuit, so this is basically swing limit. Looking at the circuit, can you tell like which transistor has which transistor can actually go out of saturation? Which do you think will be that transistor? Can M1 ever go out of saturation?
No, sir. Never
Why?
will go. It will go because drain and gate are shorted. It can be either saturation region or a cutoff region. It would be.
Can it go to cutoff?
Yeah, maybe if it drain and gate are saturation, these two conditions are only possible.
No, that's what I'm asking. In this
No,
circuit,
no, no, no.
M
It won't
go to
be. It won't be.
why?
It will be in saturation region, not cutoff.
Why it can't go to? Okay, for triode, I'm convinced since gate and drain are shorted, and drain can go one threshold below the gate, so it can't go out of it can't go in linear region. But why it can't go in saturation? That's what I'm. Why it can't go in cutoff?
Sir, it should be in that case. It should be less than threshold voltage.
What VGS, right?
Yes.
Or the current through this transistor should go to zero. Can it happen?
No. Here already
Why?
micro. 100 microamperes current source is.
Yeah, so 100 microamp fixed current is being pushed into transistor M1, which cannot change. Hence, the operating conditions of M1 cannot change with the input swing. So, your transistor M1 cannot go out of saturation. What about transistor M3? When will it go into saturation? When can it go out of saturation?
Sir, if the drain voltage, 1 point voltage is getting changed, then it will go to saturation to cutoff as triode region.
Okay, so in what case when the input goes up or input goes down? In which case this okay, yeah. So drain will go below 1 volt. How I'm saying it is basically Vi over here is some voltage, and V out is basically following that voltage, and V out in nominally is at 1.5 volt. So if Vi and this gate of this transistor is at 1.5 volt, correct? And what we know is for an NMOS to go into triode, your drain can go at least one threshold below your gate voltage. Okay, and if gate voltage is 1.5 volt, so what is the minimum value that drain voltage can attain? That is the drain voltage, the gate voltage minus one threshold, that is zero point 0.5 volt. So this drain voltage, which also happens to be your output voltage, can go up to 1 volt, correct?
Yes,
So
sir. VD means.
for this to happen, what amplitude of Vi should be? So that there is one condition of possible swing limit is M3 going into triode. Okay, so for this, your VO plus 1.5 volts should be greater than or equal to 1 volt, correct? That means to say,
Here we are
no,
we
be
are
greater
adding.
minus zero point 0.5 volts, and that means that if VO is and since we know that gain of this circuit is 1, so Vi must be greater than minus zero point 0.5 volts. So based on the first limit, and if Vi is like assumed to be a sinusoidal voltage, so the amplitude of Vi can only be less than zero point 0.5 volts. Do you follow? Assuming Vi to be sinusoidal.
Sir, sir, I mean, V out is nothing but drain voltage, no, sir.
Yeah, drain voltage for transistor M3.
Okay. Then we are writing gate voltage right side, right?
Gate voltage, okay, that basically you can do like any way you want. So basically, you need to ensure that Vd must be greater than or equal to Vg minus Vth.
Hmm.
Okay, or you can write it as Vg minus Vth must be less than or equal to Vd. These two are same thing.
No, no, sir. My question is, while we are doing this, we need here both we need to write both the DC voltage and small signal as well, right?
Yeah. So where will both DC and small signal come? Like your VG is fixed, right? The VG
Yes.
of transistor M3, that is fixed.
Mm.
That is fixed to 1.5 volts, correct?
Yes, sir.
So like which particular node is varying? It's the just the drain voltage of transistor M3, right?
Yes, sir.
So drain voltage of transistor M3 is basically the operating voltage, that is 1.5 volts, plus your output voltage, that is V naught.
Mm.
Okay. So, and Vg is 1.5 volt, Vth is zero point 0.5 volt. So, basically 1 volt must be greater than equal to 1.5 volts plus V naught. So,
Mm.
from here you get V naught must be greater than or equal to minus zero point 0.5 volts.
Okay, okay. Sir,
Okay.
getting sir. Sir,
So,
if the
yeah,
VG is varying, then we include VG, then we ignore the VD, right?
yeah. So, in this case, Vg is not. So, basically, for each transistor that you suspect can go into triode, you have to write that boundary condition of the triode. So that will contain the gate voltage of that transistor and the drain voltage of the transistor. And like depending on the circuit, if the both the gate and the drain voltage are varying with some like gain, you will substitute that gate and drain voltage with the fixed voltage, that is that it has, V fixed, plus whatever small signal voltage, V small,
Mm.
whatever small signal voltage is riding on top of that. you will substitute it in this boundary condition, and from there you will find out what is the constraint that is present on input voltage.
Sir, at the time, if we don't consider drain voltage, right?
Sorry, no, I didn't get it.
No, sir. Means while doing the assignment, also getting confused. Means while we are calculating the peak voltage,
Okay.
maximum. Sir, here in this case, drain voltage is varying. So we consider drain voltage. We ignore only fixed DC voltage. We don't consider a small signal voltage, small VG, right?
Yeah, because small VG is zero in this case.
Oh yes, yes, correct. Yeah, got it. Yeah.
Okay. So okay, the in the next okay, so transistor M3's boundary limit we have fixed. Okay, now let's go to transistor M2. Here you will see that your drain voltage is fixed to VDD. Okay, your drain voltage is fixed to VDD and your gate voltage is swinging. So in this case, what how you will write it as your for the second condition, transistor M2 to triode, VD must be greater than or equal to VG minus VTH. Correct? Now VD is fixed at 6 volts, that is VDD. You understand?
Yes, sir. In this case, VG is varying, right?
Yeah, in this case, VG is varying. So basically, 6 volts is greater than or equal to VG is 1.5 volts plus the input minus VTH. Okay.
Mm. Yes, sir.
So from this, you get the condition as, and VTH is equal to zero point 0.5 volts. So you get condition as your Vin must be less than or equal to 5 volts.
Mm. Yes, sir.
You understand?
Yes, sir. Sir, it is peak to peak voltage only, right?
Yeah. So from this condition, you get Vin is less than 5 volt. From the upper condition, you get Vin is less than zero point 0.5 volt. So if you have multiple condition, you will choose the whichever is the minimum one.
Yes, sir.
Okay. Now in this case, I have not considered transistor going into cutoff. Can you tell me why?
Uh, Sir, because of biasing, right?
Sorry, I didn't get you.
Here, for
Can
M1 transistor,
is there any transistor that can go into cutoff in this particular question?
no, sir.
Why?
Uh, be- because M1 is a saturation condition, so 1.5 voltage is maintained. If we decrease the uh, uh, drain voltage
Okay,
of M3,
see, a gate source voltage of transistor M3 is fixed, so that
mm,
cannot go into cutoff, and same is the case with transistor M1. What about
mm.
transistor M2?
So transistor M2 also 1.5 only, right? Gate to source voltage is same, right?
Okay, so like, is it varying or is it fixed?
Yeah, it is fixed, no, sir. For three transistors, gate to source voltage is 1.5 only.
Why it is fixed? Your gate voltage is varying because you have input added. Your source voltage is also varying. Still, your gate source voltage is fixed. Is it?
Yes, sir.
Why?
Because of common drain, sir.
Yeah.
Common
So
drain.
what about common drain?
Because of our common drain configuration.
So here the gain from input to output is one, right?
Yes, sir.
So wherever the gate voltage of the transistor goes, the source voltage follows the same. So your gate source voltage, your VGS of M1 is basically 1.5 volts. Sorry, 3 volts plus VI minus 1.5 volts plus V out. Okay. And since Vi is equal to V out, so your gate source voltage is fixed to 1.5 volt. You understand?
Yes, sir. Yes, sir.
Okay, so here, since your gate source voltage is not changing, so your transistor can't go in cutoff. Even if there was some output resistance over here, so let's say there was some output resistance of value Rs over here. In that case, also your VGS change will be very small. It will be basically input divided by 1 plus GM times Rs. Okay, so you can while doing the swing limit calculations, you can keep it as a guideline that it is rarely that your so basically in common drain amplifier, input transistor generally don't go in cutoff. And why is it so? This is because your gate and source voltages are following each other, and hence the VGS going below the threshold voltage is extremely rare. So, even if there is some RS at the source side, still the limit that you will get from that will be much, much higher from limit as compared to the limit that you get from the other transistors going into. Till the time this limit is reached, your other transistors would already have gone into triode. So this condition generally you don't need to evaluate in common drain amplifier. So you can keep it as a guideline while solving the questions. You understand?
Yes, sir.
Okay. So now let's come to the constant GM bias circuits that we have understood in our lectures. So can you help me? Can any one of you help me draw the constant GM bias circuit and NMOS constant GM bias circuit? So basically there is a transistor, there is an NMOS transistor M1. In this circuit, I want its GM to be fixed to a certain value of resistor, that is 1 by R. Okay. So how will I do that? If let's say can you give me some equations of the value of GM of a transistor in saturation?
Sir.
Can you what equations of GM you know in what equations of GM you know for a transistor in saturation? Can you list them for me? So one of them is GM is equal to square root 2 mu n Cox W by L times ID. Other is 2 ID by V over drive. There is one more. So one more equation is basically you have mu n Cox W by L times V over drive. So so we will try to use the second equation in order to fix the in order to build the circuit. So you need some GM that is equal to 1 over R. That means whatever you need to fix the current of this circuit in such a way that so GM is equal to 1 over R is equal to 2 ID over V over drive. Okay. So in this, what you need to maintain is you need to maintain the like vary. V overdrive basically will vary in some particular fashion due to changes in the temperature, change in the mobility or the threshold voltage of the transistor. You need to you need to vary the current id in this transistor in such a way that the that your ratio of id over v overdrive remains constant. So and 2 id over v overdrive is equal to 1 by r, where r is some external resistance. This is the fundamental that you need to maintain in this constant gm bias circuit. So from here you get id is equal to v overdrive by 2r. This is the current that you need to generate. Okay, you understand?
Yes, sir.
So let's say somehow I generated this current id equal to v overdrive by 2r. Okay, so if this current I am pushing in the circuit, and somehow let's say there is some external circuit that is biasing the gate of this gate of this transistor. So the voltage that will generate at this gate is V overdrive plus VTH, where VTH is the threshold voltage of this transistor. You understand?
Yes, sir.
You understand, right? So
Yes, sir.
now let's say I have another transistor over here. I push the same ID into it, and this transistor is basically, if this has a width over length of w by l, this transistor has 4 times w by l. Okay, now if this is 4 times w by l, what is vgs of let's call this transistor m2. If this has a width of 4 times w by l of transistor m1, what is vgs2? So if vgs1 is equal to v over drive plus vth, your VGS2 is it's not basically VT plus 2 overdrive is we shall calculate it. So I am saying that the current in both the circuits is the same, right? So ID is equal to for transistor M1, ID is equal to half mu n Cox W by L times V over drive plus VTH minus VTH whole squared. And for transistor M2, ID is equal to half mu n Cox 4 times W by L plus VGS2 minus VTH whole squared. If you divide the two equations, you will get VOV plus, this can be cancelled. So you have VOV whole square, VOV squared divided by 4 times VGS2 minus VTH whole squared is equal to 1. So from here you get VGS2 as VOV2 plus VTH. Okay, you understand till here?
Yes, sir.
Okay, so if VGS2 is VOV2 plus VTH, what will be the source voltage? This voltage is VOV plus VTH. What will be this voltage?
Sir, down, sir, down. Two times of
So this will be VOV plus VTH minus VGS2. You understand?
Sir, could you please repeat again, sir? I'm not getting.
So yeah, if basically this source volt, this gate voltage is VOV plus VTH, your
Yes, sir.
source voltage will become VOV plus VTH minus VGS2, where VGS2 is the gate source voltage of transistor M2.
Hmm.
Okay, so this voltage is equal to VOV plus VTH minus of VOV by 2 plus VTH. This is equal to VOV by 2.
Hmm.
Okay. Now, if this voltage is VOV by 2 and I place a resistance of value R at this node, so what will be the current that will be flowing through this resistance?
Yeah, VOE by 2 R, sir.
VOV by 2R,
Hmm.
which is exactly the current that we wanted to push in the transistor M1 was.
Yes, sir.
Okay. So now you have got this current. You need to mirror this current from this circuit to this circuit. What will you use?
Sir, we short gate and drain.
Which gate and drain? You need to mirror. So this is a current. So this is a current of value V over drive by 2R flowing through this transistor. You need to mirror this current into this branch of in the branch of transistor M1. So what will you use? What is the circuit that you use to mirror the current?
Yeah, sir, we short drain gate and drain of M2 to get the same current of to M1.
Will that work? But that will just how will that work?
Uh, me-
I will redraw this image. So far we have developed this circuit. This is M1. This is M2. M1 has a width by length ratio of W by L. M2 has width by length ratio of 4 times W by L. You have a resistor with value R over here. This voltage is VOV by 2. The current that is flowing through this complete branch is VOV by 2R. And whatever current is flowing, this ID equal to VOV by 2R, you need to mirror it in transistor M1 as well. So just forget about it. Let's say I had a current of I and I wanted to mirror it in this transistor. Okay. Or I wanted to mirror in some other branch. What will I use? So there are two current mirrors that are available to us, right? One is the PMOS current mirror, one is the NMOS current mirror. The PMOS current mirror behaves this way, that if you have a I that is coming from VDD and going downwards, then you can use this NMOS current mirror and mirror this current of value I. Okay. And then if you have alternatively, if let's say you have a current that is like going to ground and coming from some other place and you need to mirror this, you need to use a PMOS current mirror. And wherever this circuit will connect, that basically will have I current in it. Okay. So out of this and this, which one can you use in this particular the red circuit? This is A, this is B, the second one. Okay.
PMOS.
No, yeah, correct. PMOS. So this ID of V overdrive by 2R, you need to bring in the transistor M1. So what you will use is, you will use a PMOS current mirror for that. So here the current is generated. This is the current, this is the branch where current is generated. So here you will have the diode connected PMOS, and the current that needs to flow, that current needs to be pushed in transistor M1. So in this case, you will have a open one. Okay. Now, in order to generate the VGS of this transistor, you will just short this thing like this. Okay. You understand the circuit?
Yes, sir.
So here you have basically VGS, that is equal to V over drive plus VTH. The current that is being pushed into the circuit is basically ID is equal to V over drive by 2R. So your GM, that is 2ID by V over drive, is equal to 1 by R. Now let's say for some reason your V overdrive changes. Okay. V overdrive can change due to change in threshold voltage or change in the mobility of your chip. So due to some reason your V overdrive has changed. Now if your V overdrive changes, this voltage, that is V overdrive by 2, will also change, and this will make the change in the current ID in such a way that ID over V overdrive still remains constant, that is equal to 1 over R. So this is your constant GM bias circuit. So you have W by L over here, a resistance over here, and this is 4W by L. So this is how you build your constant GM circuit. Now let's consider back channel effect in this particular circuit. Is every one of you, sorry, back gate effect. Is every one of you familiar with back gate effect?
Sir, I'm not
You
familiar,
know
sir.
about the quantity called GMBS?
Yes, sir. When body is when yeah,
What is
when
it?
body is considered, then we'll consider GMBs, right?
Correct. Body is acting as a second gate. So what happens is, generally in your CMOS technologies, you basically have a common body for multiple transistors. So generally, while initial study of your analog electronics, what we assume is your there a transistor is a four terminal device. You know about this, right? So in four terminals, in initial studies, what we assume is your body and your source are connected to each other. Okay. That means to say, basically this is how it looks on the silicon. You have a oxide layer, you have a metal layer, this is a substrate layer, and let's say this is NMOS, so this will be a P substrate layer. You will have N plus doping over here, N plus doping over here, and this is the body terminal. Okay. So this will be basically with a P plus doping. This will be body terminal, this will be your source terminal, this will be your gate terminal, and this will be your, sorry, this will be your drain terminal, and this will be your gate terminal. Okay. So what happens is, generally, like in for theoretical purposes, while understanding initially in analog electronics, we assume that body and source are shorted. Okay. But when you actually design the transistors, the body, this body is basically just the p substrate, and this is common for all the transistors that are in your close vicinity. So you can't actually short your body and source. You connect the body to the VDD to ground, so that there is no so that the N plus and P region are is in reverse bias, and no current flows from these N plus diffusion region to the substrate. For that reason, you connect your body to the most negative voltage available, uh, and the source is connected to wherever the circuit demands to be, but the body is always connected to ground. So this is connected to basically some this is connected to ground, this is connected to ground. Now in this case, in transistor M1, both body and source are connected to same voltage, that is ground. Okay, but in transistor M2 this is not the case. The transistor M2 body is connected to ground, but source is connected to some different voltage. So there is a non-zero voltage that has developed between body and source. Okay, so from some initial device physics theory, you know that your body source voltage can modulate the threshold voltage of your device, right?
Yes, sir.
Okay, so threshold voltage of transistor VT, so VTH1 would not be equal to VTH2 in actual circuitry. You understand this?
Yes, sir.
The threshold voltage of two transistors will not be equal, and this is not the mismatch in threshold voltage due to random factors. This is a systematic mismatch. Why this has occurred? Because the source voltage of transistor, the source terminal of transistor M2 is not actually connected to the ground. So the threshold voltage of transistor 1 and transistor 2 are different. So let's say your transistor 1 has VTH1 is equal to VTH, and your transistor 2 VTH2 is equal to VTH plus some delta VT. Okay, you understand?
Yes, sir. Eh,
Yeah. So if this is the case, then can you again analyze this circuit? You have VDD over here, VDD over here. Sorry. W by L and 4W by L. Okay, so this has a threshold voltage of VTH1, and this has a threshold voltage of VTH2. Okay, so if let's say the same current, ID current was flowing through this. Okay, the voltage developed at this node will be V overdrive plus VTH1. Okay, where V overdrive is the overdrive voltage of transistor M1. Now due to the the current is basically mirrored by this PMOS devices, so the current still in transistor M1 and transistor M2 will remain same, because these PMOS, as long as there is no short channel effect. We are not neglecting short channel effect for now. So if short channel effect is not there, and since this mirroring is perfect, so ID in both the transistor will still remain the same. So let's try to write the equation for transistor M1. We have ID is equal to half mu n Cox W by L times V overdrive 1 plus VTH, or let's talk in terms of VGS for now. VGS1 minus VTH1 whole squared, where VGS1 minus VTH1 is considered to be the overdrive voltage V overdrive. Okay, so from here you get, and for transistor M2, so this is equation 1. For transistor M2, what you have is half mu n Cox 4W by L times VGS2 minus VTH2 whole squared. This is equation 2. Okay, and let's call VGS2 minus VTH2 as V overdrive 2. Okay, so equation 1 can be rewritten as ID is equal to half mu n Cox W by L times V overdrive whole squared. And for equation 2, for transistor M2, ID can be written as half mu n Cox 4 times W by L times V overdrive 2 whole squared. Okay, so this is, let's say, equation A and equation B. If you divide equation B by equation A, what you get is V overdrive 2 whole squared times 4 divided by V overdrive whole squared is equal to 1. That implies V overdrive 2 is equal to V overdrive by 2. So you can see that despite of change in threshold voltage of these two transistors, since the current in both the transistor is same, and the mu n Cox and all those things are same, and only the aspect ratio is basically 4 times in the transistor M2 as compared to transistor M1. So the V overdrive relation between these two transistors is still intact, and that is basically the transistor M2 has half the overdrive voltage of transistor M1. This is still intact. Now, where the problem comes is, let me copy the circuit. The problem comes over here. So this is V overdrive plus VTH1. We know that the overdrive voltage of transistor 2 is still V overdrive by 2. So what is VGS2? Can you tell me VGS2? It's basic. It's plus VTH, not minus VTH, and V overdrive by 2 plus VTH2. Okay. So if the transistor VGS2 is V overdrive by 2 plus VTH2, so what is this voltage now? This voltage is V overdrive plus VTH1 minus V overdrive by 2 plus VTH2. Okay, so this is equal to V overdrive by 2 plus VTH1 minus VTH2, that is equal to V overdrive by 2 plus, sorry, minus delta VT. Why? Because initially we said that VTH2 is basically VTH plus delta VT, and VTH1 is equal to VTH. So you see that there is one extra term that has popped up in this the voltage expression at the source of transistor M2. And if we calculate the current now, so ID will be now equal to V overdrive by 2R plus, sorry, minus delta Vt by R. Okay, if this is the ID, this same ID is mirrored in transistor M1 also. So transistor M1's, basically GM of transistor M1 is 2ID by V over drive, that is equal to 2 times V over drive by 2R minus delta Vt by R divided by V over drive, which comes out to be 1 by R minus 2 delta V by R times V over drive. Okay, so this term is constant. Okay, this term won't depend on like, as long as this resistor is fixed, this term won't depend on the PVT, the voltage and temperature variation. However, the change in threshold, that is the delta Vt or the overdrive voltage, will definitely depend on the temperature and process changes. So in this case, there will be, and this delta Vt won't be very high, but still it will be non-zero. So in this case, your GM1 won't exactly be fixed. Like, you were supposed, you wanted it to be fixed to 1 by R, but it won't be fixed to 1 by R. It will be 1 by R minus 2 delta Vt by R times VOV. And since delta Vt and VOV both will change with temperature and process, so your like GM won't be completely fixed GM circuit. There will be some non-ideality in this. So let's try to find another circuit which can alleviate this particular non-ideality. So what was the first reason for which this non-ideality came?
Sir, because of VT.
Yeah, why did the VT of the two transistors change?
Because in the M1 transistor, here source is directly grounded. In this case, source is has some voltage and body. Because of that, body effect will come into picture.
Body and source are not at the same voltage. So
Hmm.
it looks like if we somehow make both the transistor M1 and M2 to be ground, both the sources of transistor M1 and M2 to be grounded, then our problem will be solved, right? In that case, VTH of both transistor M1 and M2 will be same, and your basically you will have lesser variation, like that body source. The body source, like the backgate effect, will go away. Correct.
Yes, sir. So in that case, M1 will also, we need to make source, right?
Okay, that, or let's try to eliminate the source, the body source. Let's try to short both the body source of both transistor M1 and M2. So let's try to build that circuit. So this is M1 with W by L, and this transistor is M2 with 4 times W by L. Again, since the current in both the circuits have to be same, so there will be a current mirror that will still remain at the top. Okay, so assuming that this is some current ID, the same current ID is flowing over here. Now you want to generate a voltage, so this should have VOV, and like, if, like, somehow, let's say somehow we have attained some kind of feedback configuration that this transistor, that the gate source voltage of transistor M1 is VOV plus VTH, and the gate source voltage of transistor M2 is VOV by 2 plus VTH. So we need to somehow create this scenario. Okay, so if, let's say, there was a resistor R over here, okay, if current ID flows through this resistor, what is the potential difference that is generated in this across this resistor? It's basically ID times R. Correct.
Yes,
You
sir.
understand this, right?
Yes, sir.
So basically what we want is VOV plus VTH minus VOV by 2 plus VTH. That is the difference between the gate source voltage of transistor M1 and gate source voltage of transistor M2. That comes out to be VOV by 2 shall be equal to ID times R. Then only you will have ID is equal to, then only you can say that 2ID by VOV, that is equal to GM, that is equal to 1 by R. So this condition you need to satisfy in the circuit. You understand?
Yes, sir.
Hmm? You understand this, right?
Yes, sir.
Okay. So if this condition you need to satisfy in this circuit, what you will have to do is basically, let's say if I connect the gate of transistor M2 to this and the gate of transistor M1 to this thing. Now, basically, like this potential difference across this resistor, I have made sure that it is equal to the gate source voltage of transistor M1 minus the gate source voltage of transistor M2. And I push current of value ID into this. So is this equation that I wrote over here, this is basically VGS1, this is VGS2, and VGS minus VGS1, basically VGS1 minus VGS2 is equal to ID times R, and that is equal to VOV by 2. So my condition is satisfied over here, right? Okay, everyone understood this point?
Sir, sir, could you repeat again, sir?
From where did you not follow this?
Sir, by by connecting M1 gate to the drain.
M1
You
gate to the, okay,
drain.
so basically you had till this point you understood, right? If you are pushing ID into this resistor, so the voltage difference across this resistor is ID times R. And this
Hmm.
ID times R, you want to make sure that this ID times R is equal to the difference between the gate source voltage of transistor M1 and the gate source voltage of transistor M2.
Yes, sir.
Okay, from this particular equation. Okay.
Yes. Yes, sir.
So, like to achieve that, this is the gate source voltage of transistor M1. You connect it over here, and this is the gate source voltage of transistor M2. You connect it at the bottom of this resistor. So, the potential difference, that is ID times R, equal to VGS1 time minus VGS2 is satisfied in this, right? Now, this
Hmm.
is VGS1, this is VGS2, and this particular equation is now satisfied.
Hmm. Yes.
Okay.
Yeah. Okay.
So from this you can say that like this circuit, I will redraw the circuit. This was W by L, this was 4 times W by L. Okay, so this is another variant of fixed GM bias circuit which takes care of the backgate effect. You understand? Any doubt in this?
No, sir. Perfect.
Okay. So this we have discussed, and there are other more exciting circuits that can generate fixed GM by fixed GM. So if you want to learn one of those circuit, I will paste a link in the chat window. That is a paper that discusses one of the fixed GM circuit. So this circuit actually looks quite complicated, but if you read that paper, you will easily understand how the circuit works. And basically, the circuit solves few other problems that neither circuit 1 that we discussed initially nor the circuit 2 that we discussed later can solve. For example, both the circuits basically require the square law model to work. So the GM equal to 2I over V over drive. This particular relationship comes only if the transistor is following the square law model. However, if generally the modern CMOS technologies, this condition is not satisfied, so the square law model is not valid completely. So this circuit basically solves that problem also, and moreover, this circuit basically makes the transistor immune to supply variation. You can learn more about this circuit in this paper, which is written by Professor Shanti Pavan, who is from IIT Madras only. And the name of the circuit is a fixed transconductance biasing technique for CMOS analog integrated circuits. And this is the link. This link I will share in the notes that I upload also, and I will paste it in the chat window. So uh, this is basically the circuit. You can go and read about the circuit in more detail in this paper. And if you have any doubt regarding this circuit, you can ask the same doubt in the next session. Any other doubts?
Fine, sir.
Okay. So is there no other doubt pertaining to any weak material or whatever we have discussed in this tutorial? Okay, so if there is no doubt, we can end this session. Thank you for attending.
Thank you, sir.